For centuries, humanity has listened to the silence between the stars. Then one signal arrives, too precise to be random, too distant to be human, and too old to ignore. It does not bring an invasion. It does not bring a greeting. It brings a final message from a world that may have understood its fate too late. Before the story begins, please like this video, subscribe to the channel, and stay with this quiet journey into the first contact humanity was never prepared to receive. In the outer regions of the Milky Way, far from any single point of attention, the galaxy extends in a slow and steady structure of stars, gas, and dust. It is a spiral system, with long arms that curve around a central bulge, each arm containing billions of stars separated by distances that are difficult to hold in simple thought. Between these stars lies a medium of thin gas and fine particles, known as the interstellar medium. It is not empty space in the strict sense, but a very sparse environment where atoms drift over vast distances and light travels largely uninterrupted. Within this wide setting, the conditions for communication are defined not by proximity, but by persistence and clarity. Radio waves, a form of electromagnetic radiation, move through this medium with little resistance. Unlike visible light, which can be scattered or absorbed by dust. Radio waves of certain frequencies pass more easily across long distances. For this reason, scientific efforts to detect signals beyond Earth often focus on this part of the spectrum. Observatories on Earth, as well as instruments placed in orbit, are designed to monitor these frequencies continuously, scanning the sky for patterns that differ from natural emissions. These patterns are expected to stand out through repetition, structure, or mathematical consistency. Natural sources of radio emission are many. Stars emit radiation due to their heat and magnetic activity. Pulsars, which are rapidly rotating neutron stars, produce highly regular pulses that can appear artificial in their precision. Clouds of gas emit radiation at specific frequencies depending on their composition. Even the background of the universe contributes a faint, steady signal that fills all directions. To distinguish an artificial signal from these natural sources requires careful filtering, long observation times, and comparison across multiple instruments. The galaxy itself rotates slowly, carrying stars and their systems along defined paths. The position of any star relative to Earth changes over time. Though on human scales this motion is subtle, still, when observing distant signals, scientists account for this motion by adjusting for Doppler shifts, a change in frequency caused by relative movement. This allows a signal to be traced back to a fixed region in space, even as both source and observer continue their motion within the galaxy. Beyond the spiral arms, the galaxy thins into a halo where stars are fewer and older. The density of material decreases, and the environment becomes quieter in terms of radio noise. However, most observations focus on the denser regions where stars are more numerous, and the chance of complex systems is higher. These regions contain a mix of young, bright stars and older, cooler ones, along with planets, debris, and the remnants of earlier stellar generations. Distances in the galaxy are measured in light years, a unit that describes how far light travels in 1 year. This distance is approximately 9 trillion kilometers. When signals are detected from sources thousands of light years away, they represent events that occurred thousands of years in the past. The time delay is a fundamental part of interstellar communication. Any exchange is not immediate but extended across generations. This delay shapes the interpretation of any signal, as it reflects a state of the source that may no longer exist in the present moment. The background noise of the galaxy forms a constant field against which all signals must be detected. This noise includes emissions from stars, gas clouds, and distant galaxies. It varies in intensity depending on the direction of observation and the frequency used. Sensitive instruments are required to detect faint signals within this noise. These instruments often operate in remote locations, away from human-made interference, or in space, where the atmosphere does not distort incoming waves. Human technology also contributes to the radio environment. Signals from Earth, including communications, broadcasts, and radar, extend outward into space. These signals weaken rapidly with distance, but they form a shell of emission around the planet that expands over time. Beyond a certain distance, these signals become indistinguishable from the background noise. This illustrates the challenge of detecting similar signals from other sources. Only those that are strong, focused, or repeated over long periods are likely to be distinguishable. Within this vast and layered environment, the search for artificial signals continues with patience and precision. Observatories scan narrow bands of frequency, recording data that is later analyzed for patterns. Algorithms are used to detect anomalies, but human oversight remains important to interpret the results. False detections occur, often caused by terrestrial interference or known astronomical sources. Each candidate's signal is examined carefully before it is considered significant. The concept of a signal from an unknown origin rests on the idea that an advanced system may choose to transmit in a way that can be recognized by others. This often involves the use of simple mathematical sequences or repeating structures that are unlikely to arise from natural processes. Such patterns would be embedded within the signal, allowing it to be identified even if the content is not immediately understood. The outer galaxy, with its immense scale and steady processes, provides the setting for this search. It is a region defined by distance, motion, and quiet persistence. The conditions for communication are shaped by physics that applies equally across all locations. Light travels at a constant speed. Matter interacts in predictable ways. Energy is conserved and transformed according to known principles. Within this framework, any deviation from natural patterns becomes a point of attention. As observations continue, the data accumulates. Years of recording build a map of the radio sky, revealing both expected and unexpected features. Most signals are catalogued and understood within existing knowledge. A small number remain unexplained for a time, then are resolved with further study. The process is gradual and careful, avoiding premature conclusions. In this outermost region of the narrative, nothing is yet certain beyond the structure and behavior of the galaxy itself. The silence is not absolute, but it is dominated by natural processes that follow known laws. The search is ongoing, grounded in observation and guided by the expectation that any true signal of external origin will reveal itself through clarity and repetition. The galaxy remains vast, its many regions unfolding in slow motion, each contributing to a background that is both complex and stable. At the outer edge of the solar system, the sun no longer appears as a broad source of warmth but as a bright star among other stars. Its gravity still reaches far beyond the planets, holding distant icy bodies in long and quiet paths, yet its wind of charged particles becomes weaker with distance. This wind, known as the solar wind, flows outward from the sun in all directions. It carries electrons, protons, and magnetic fields into space, forming a large protective region called the heliosphere. The heliosphere is not a solid wall, it is a moving boundary shaped by pressure, motion, and the surrounding interstellar medium. the solar system moves through the galaxy, and this motion affects the shape of the heliosphere. The Sun and its planets travel through a thin flow of interstellar gas. As the solar wind expands outward, it meets this external material. The meeting does not happen suddenly, but across broad zones where particles slow, change direction, and mix. At great distance from the Sun, the solar wind loses strength until it can no longer push freely outward. This region is called the termination shock, where the solar wind slows from very high speed to a slower and more disturbed flow. Beyond this region lies the heliosheath, a broad layer where the solar wind is compressed and irregular. Particles move in complex ways. Magnetic fields bend and fold. Energetic particles from outside the solar system enter more easily, though some are still slowed or deflected. These high-energy particles are known as cosmic rays. They originate from sources such as exploded stars and active regions beyond the solar system. The heliosphere reduces some of their intensity near Earth, so its outer boundary has direct importance for understanding the radiation environment around the planets. Farther outward, the heliopause marks the place where the solar wind and the interstellar medium reach a balance. It is often described as the boundary of the Sun's influence in space, although gravity extends much farther. The heliopause is not a perfect sphere. It shifts with changes in solar activity and pressure from interstellar gas. It may ripple and vary over time, responding to the solar cycle, which changes over about 11 years. When the Sun is more active, the solar wind can push outward with greater strength. When it is quieter, the boundary can move inward. Human understanding of this distant region comes from a small number of spacecraft and from remote observation. The Voyager spacecraft, launched in the 20th century, travel through these outer zones and provide direct measurements of particles and magnetic fields. Their instruments detect changes in the density of plasma, the behavior of energetic particles, and the direction of magnetic fields. These measurements help identify when a spacecraft passes from the solar wind into interstellar space. The data arrives weekly because the spacecraft are extremely far away, yet it remains valuable because no other human instrument has made the same journey. At these distances, communication with spacecraft becomes a precise and patient act. Radio signals sent from Earth travel at the speed of light, yet the time required for a command or response spans many hours. Antennas on Earth must aim with great accuracy, and receivers must separate the spacecraft signal from background radio noise. The signal is faint, but its origin is known, its structure is known, and its timing is expected. This makes it different from an unknown signal, which must first be recognized without prior agreement. Still, the same principles apply. A weak transmission becomes meaningful when it carries structure, direction, and repeatability. The heliosphere also acts as a filter for signals and particles entering the solar system. Radio waves pass through this region with little obstruction at many frequencies, but charged particles interact with magnetic fields. Dust grains move according to gravity, radiation pressure, and electromagnetic forces. Neutral atoms from the interstellar medium can enter more directly because they are not strongly guided by magnetic fields. These atoms help scientists study the material surrounding the solar system. By measuring them, researchers learn about the local interstellar cloud, a region of gas through which the Sun is currently moving. The outer solar system contains more than boundaries. It also holds the Kuiper Belt, a region of icy bodies beyond Neptune. These objects are remnants from the early formation of the solar system. They preserve frozen materials, including water ice, methane, ammonia, and other compounds. Their orbits reveal the history of planetary migration and gravitational disturbance. Some are small and dark. Others, such as Pluto, are large enough to have complex surfaces and thin atmospheres that change with distance from the Sun. In the context of listening for signals, these bodies form part of the quiet outer landscape through which any incoming transmission must pass. The cold in these regions is deep, but temperature in space is not felt as it is in air or water. Objects gain and lose heat through radiation. A surface facing the distant Sun receives little energy, while shaded areas can remain extremely cold. Space itself contains particles, but they are too sparse to carry heat in the familiar way. Instruments must be protected from both cold and radiation, and spacecraft must use stored power or nuclear heat sources to continue functioning. The solar system edge is therefore a transition zone. It is neither the familiar planetary region nor the open interstellar medium. It is a place where the Sun's outward flow becomes tired and disturbed, where outside particles press inward, and where human instruments become rare and distant. It is also the first inner layer through which any signal from beyond must be understood. A radio wave arriving from the galaxy crosses this boundary without drama. But the knowledge of the boundary matters because it defines the local environment of detection. In this region, the scale of the search changes. The galaxy remains vast behind it, but the solar system begins to take form as a physical place with its own shield, motion, and surrounding materials. The silence of interstellar space gives way to the faint presence of the Sun's outer breath. Measurements remain slow and careful. Each particle count, each magnetic reading, and each weak transmission from a distant probe adds detail to the shape of the boundary. The path inward continues through a region defined by gradual pressure, sparse matter, and the steady movement of signals across distance. Beyond the orbit of Saturn, and within the long reach of the outer planets, the solar system becomes a wide field of dim light. Slow movement and careful observation. Jupiter, Saturn, Uranus, and Neptune occupy immense paths around the Sun, each surrounded by moons, rings, magnetic fields, and faint streams of dust. Their distances are large enough that sunlight arrives weakened, yet strong enough to reveal cloud bands, icy surfaces, and the outlines of distant worlds through patient instruments. In this region, scientific attention depends on telescopes, spacecraft records, and long-range tracking systems that measure motion and radiation with high precision. The outer planets are not quiet in a simple sense. Jupiter produces intense radio emissions from its magnetic field and from the movement of charged particles around its moons. Saturn also creates radio waves and plasma activity within its magnetic environment. Uranus and Neptune, though farther and less studied, possess magnetic fields that are tilted and uneven compared with their rotation. These natural emissions form part of the background that scientists must understand when searching for unusual signals. A pattern from beyond Earth cannot be judged in isolation. It must be compared with the known behavior of planets, moons, and plasma in the outer solar system. Jupiter dominates much of this region through gravity and magnetism. Its mass is greater than that of all the other planets combined, and its gravity influences small bodies, comets, and spacecraft trajectories. Its magnetic field is vast, extending millions of kilometers into space. Charged particles trapped within this field move at high energy and interact with the Moon, Io, where volcanic activity supplies sulfur and oxygen ions. These particles produce radio emissions that can be detected from Earth. Their behavior is powerful but not random. It follows physical processes linked to rotation, magnetic field structure, and moon positions. Saturn presents a different kind of system. Its rings form broad, thin structures made mostly of ice particles, ranging from tiny grains to larger fragments. These rings reflect sunlight and interact with Saturn's moons through gravity. The planet's magnetic field is more aligned with its rotation than Jupiter's, yet it still shapes a complex environment of charged particles. Instruments from past spacecraft missions have measured radio bursts, auroras, and plasma waves around Saturn. These signals belong to known natural processes, and they help scientists build a catalogue of what the outer solar system already produces. Farther inward from the solar system edge but still distant from Earth, Uranus and Neptune move slowly through their long orbits. Uranus is tilted so strongly that its rotation axis lies almost sideways relative to its path around the Sun. Neptune is marked by strong winds and storms in a cold hydrogen and helium atmosphere. Their magnetic fields are offset from their centres and tilted from their rotation axes, creating changing magnetic environments as they spin. These unusual structures matter because they show that nature can create complex and shifting radio behaviour without intelligence. Careful analysis must account for such variety before any unknown signal can be treated as artificial. Between and beyond these planets, spacecraft and telescopes serve as patient watchers. Some spacecraft are active, sending back data from great distances. Others have completed their missions, leaving behind archives of measurements that still support research. Telescopes on Earth and in space observe the outer planets across many wavelengths, including visible light, infrared radiation, ultraviolet radiation, and radio waves. Each wavelength reveals a different part of the system. Infrared observations show heat patterns. Ultraviolet observations reveal auroras and upper atmospheres. Radio observations trace magnetic activity and distant transmissions. The detection of a weak artificial pattern in this region begins as a problem of comparison. Instruments record large amounts of data, and most of it contains expected signals from planets, spacecraft, Earth-based interference, and the broader sky. A possible signal must appear in a way that does not match these sources. It must persist or repeat. It must show a narrow frequency or an organized sequence. It must be detected by more than one instrument or at more than one time. Without these checks, a single event remains an anomaly, not evidence. The outer planet region adds further complexity because spacecraft transmissions cross it from different directions. Command from Earth travel outward, and data from spacecraft returns inward. These signals are known and scheduled, but their reflections, side effects, or interference patterns can sometimes create misleading features in observations. Ground stations use exact timing, frequency records, and spacecraft positions to identify these known signals. This careful accounting prevents ordinary human technology from being mistaken for something beyond human origin. Dust also moves through this region. Tiny particles from comets, collisions, and rings drift in space, shaped by sunlight, gravity, and electromagnetic forces. Dust does not usually block radio waves, but it contributes to the physical environment. It marks the history of small bodies and impacts. It helps reveal the pathways of debris and the slow grinding of materials over time. In a scientific search, even this faint dust has meaning because it reminds observers that the solar system is active at many scales. Comets pass through the outer planet region on long orbits. Some come from the Kuiper belt, while others may originate from far more distant reservoirs of icy bodies. As comets approach the Sun, frozen materials change directly into gas, releasing dust and forming glowing comas and tails. Far from the Sun, many remain dark and inactive, small frozen bodies moving silently through wide space. Their paths can be altered by planetary gravity. Their materials preserve early solar system chemistry. Their presence adds another natural layer to the environment through which signals and observations must be interpreted. In this section of the solar system, the sense of scale remains broad but more structured than the heliosphere. There are worlds with atmospheres, moons with ice and rock, rings made of countless particles, and magnetic fields that create natural radio voices. Scientific instruments do not simply listen into emptiness. They listen through a known landscape of planetary activity. Every signal must be placed against this landscape before it can be understood. The first unusual pattern, at this stage, is not yet a message in any human sense. It is only a measured feature that appears in records taken while observing the outer planet region. It is narrow, repeated, and not easily matched to Jupiter, Saturn, Uranus, Neptune, known spacecraft, or terrestrial interference. Its strength changes with Earth's rotation and telescope pointing, suggesting a direction in the sky rather than a local source. It remains faint, and caution governs every statement about it. Observations indicate that it is structured. It remains uncertain whether the structure is artificial, instrumental, or caused by an uncommon natural process. The Outer Planet Watch continues, steady and patient, holding the signal within a wider field of known worlds and known noise. Inside the outer planet region and closer to the Sun, the inner observing network becomes more active, more crowded, and more precise. Earth is still only one planet among several, but it is the center of human measurement, and its instruments form a layered system of antennas, optical telescopes, space observatories, timing laboratories, and data archives. Around the planet, satellites move through low orbit, medium orbit, and distant paths. On the ground, large dishes turn slowly towards selected regions of the sky. In this inner network, an unusual signal is no longer only a faint pattern noticed among distant planetary emissions. It becomes a measurement problem shared across many systems. Radio astronomy depends on the careful collection of weak electromagnetic waves. A radio telescope uses a large reflecting surface or an array of smaller antennas to gather incoming waves and focus them into receivers. The receivers convert the faint energy into electrical signals that can be recorded and analyzed. The larger the collecting area, the more sensitive the instrument can be. Arrays of antennas can work together through a method called interferometry, which combines signals from separated instruments to create sharper views of the sky. This technique allows scientists to locate sources with far greater accuracy than a single dish can provide. The inner network is also shaped by time. Atomic clocks, which measure time through stable changes in atoms, allow observatories to compare signals with extreme precision. When an incoming wave reaches one antenna slightly before another, that delay helps determine the direction from which the wave arrived. The delay is tiny, but it can be measured. By comparing many antennas across Earth, scientists narrow the possible location of a source. The process is slow, not because the mathematics is vague, but because every local effect must be checked. The Earth rotates, the atmosphere changes, instruments warm and cool, human transmitters produce interference. Each detail must be removed or accounted for before the sky itself can be trusted. The atmosphere is both a shield and an obstacle. It protects the surface from harmful radiation and slows many particles from space, but it also affects observations. Radio waves of some frequencies pass through the atmosphere well. Others are absorbed, distorted, or reflected by layers of charged particles in the ionosphere, a region of the upper atmosphere influenced by solar radiation. Water vapor, storms, and temperature changes can affect measurements at other wavelengths. For this reason, space observatories are placed above much of the atmosphere, where they can observe infrared, ultraviolet, X-ray, and gamma-ray radiation more clearly. Ground and space instruments together form a more complete view. When the unusual signal enters the records of the inner network, the first task is not interpretation. The first task is exclusion. Scientists compare the timing with satellite transmissions, aircraft systems, radar activity, communication bands, and known spacecraft. They check whether the signal appears when an antenna points toward the same sky position on different days. They examine whether it disappears when the telescope points away. They review maintenance logs, weather data, receiver behavior, and nearby transmitters. A signal that survives these checks becomes more interesting but not yet conclusive. The signal is observed in a narrow band, meaning its energy is concentrated near a specific frequency instead of spread broadly across many frequencies. Many natural sources produce wide emissions, though some natural processes can create narrow features. A narrow band is therefore suggestive but not decisive. The signal also shows repeated timing, with intervals that remain stable after corrections for Earth's motion. This stability matters because Earth's rotation and orbit change the observed frequency slightly. If a signal comes from space, its frequency appears shifted as Earth moves toward or away from the source. Correcting for this motion helps reveal whether the pattern belongs to the sky or to Earth. Several observatories attempt to observe the same region. Some detect the pattern faintly, others do not, because their sensitivity, sky coverage, or observing schedule differs. This uneven result is common in astronomy. A source may be weak, intermittent, or visible only under certain conditions. The absence of detection by one instrument does not automatically erase the evidence from another, but it does require caution. Records are compared with care, and claims remain modest. Observations indicate that the signal has structure and direction. It remains uncertain whether the source is technological. The inner planet network also includes optical and infrared surveys. These surveys map stars, asteroids, comets, and transient events, which are short-lived changes in brightness. If a radio source appears in a certain direction, telescopes search that region for stars and known objects. Catalogues built over many years provide positions, distances, colours, and motions. A signal without a visible source is not impossible, because many stars are faint or obscured. But any possible counterpart helps guide the analysis. The sky position is compared with stellar catalogues, dust maps, and known radio objects. Each match is tested rather than assumed. Mars, Venus, Mercury, and the Moon also belong to the inner system of observation. Spacecraft orbiting these bodies send regular signals back to Earth, and their paths are known. The Moon reflects some radio waves and can block parts of the sky during observations. Mars missions communicate in scheduled windows. Venus and Mercury are studied by radar and spacecraft, though their positions and motions are predictable. These nearby worlds create a managed environment of known signals. Their presence requires discipline, because a reflection or side lobe from an antenna can sometimes place a known source where it does not belong in a first reading. The deep space antennas on Earth are designed to communicate with spacecraft and to receive very weak signals from distant missions. They operate with exact frequencies, coded transmissions, and known timing. Their experience with faint spacecraft data gives scientists practical knowledge of how weak signals behave after traveling across space. Noise, loss, and delay are normal. A meaningful transmission must stand above these limits through structure. In the case of the unusual signal, the pattern appears too distant in direction to belong to a known spacecraft, and its timing does not match scheduled transmissions. This finding reduces some ordinary explanations, though it does not remove all of them. Data processing becomes a central part of the work. Raw signals are stored as streams of numbers, representing intensity over time and frequency. Software searches these streams for repetition, drift, and correlations between observatories. A frequency drift is a slow change in frequency that can be caused by motion between source and receiver. If the drift matches a rotating planet, an orbiting transmitter, or the motion of Earth, it gives clues about the origin. The unusual signal shows a drift that can be corrected in more than one way, so the result is treated carefully. Several models remain possible. Inside this network, human interpretation remains restrained. The signal is not named as contact by evidence alone. It is a candidate, a structured radio source of unknown origin. The word candidate is important because it keeps the conclusion open. The instruments continue to listen. The data is shared among independent groups. Each group tests the same records with different methods. Agreement grows only where measurements overlap. The inner observing network holds the signal close enough for scrutiny, but not close enough for certainty. It becomes clearer as a pattern, yet still distant as a meaning. Earth's instruments turn, record, compare, and wait, while the measured sky slowly separates ordinary noise from something that may require a new category. Within the reach of Earth's most sensitive instruments, the signal arrives as a narrow line in a wide field of noise. It is not bright in the way a star is bright, and it is not loud in the way a storm is loud. It is a small concentration of energy at a specific radio frequency, appearing against the restless background of the sky. At first, it resembles many other candidate events that pass through observatory records each year. A telescope points toward a region. A receiver measures a faint rise, and software marks the change for later review. Most such marks are explained. This one remains after the first explanations are removed. The process begins with the raw record. A radio receiver divides incoming waves into channels, each representing a small range of frequency. The signal occupies only a few channels, and its strength rises and falls in a measured pattern. Its position in the data shifts slightly over time, not randomly but in a way that suggests motion between source and observer. Earth's rotation, Earth's orbit around the Sun, and the movement of the telescope all affect the received frequency. These effects are calculated and removed. After this correction, the pattern becomes steadier rather than disappearing. This behavior supports the possibility that the signal comes from beyond Earth. The next layer of examination concerns local interference. Earth is filled with human transmissions, communication satellites, navigation systems, radar installations, aircraft, ships, ground stations, and electronic devices all create radio emissions. Some are strong and obvious. Others enter through side paths, reflections, or equipment effects. Radio observatories keep records of known interference because it can imitate signals from space. Engineers compare the candidate with databases of local and orbital transmissions. They examine whether the frequency is assigned to human use. They check whether the signal appears only at one observatory or in one receiver chain. A local source would often show signs of closeness, such as appearing in many directions or failing to follow the motion of the sky. The signal does not behave like an ordinary local source. It appears strongest when antennas point toward the same celestial region. It weakens when they move away. It returns when the region rises again with Earth's rotation. This return is important, because the sky itself moves across the view of a ground telescope in a predictable way. A terrestrial signal usually does not follow that pattern. Still, reflections can be complex, and satellites can pass through antenna side lobes. So the conclusion remains cautious. The data supports an astronomical direction, but the testing continues. A second observatory detects the signal during a separate observing window. Its equipment is different, its local environment is different, and its location on Earth is far from the first. The signal appears at the expected time and at a related frequency after accounting for Earth's motion. The strength is not identical because telescope design, weather, receiver sensitivity, and source behavior all influence the result. Yet the repeated appearance in independent systems greatly increases scientific interest. A third facility records a weaker trace, close to the predicted direction but not strong enough for full confirmation. The combined evidence does not yet explain the source, but it narrows the field of ordinary errors. Natural explanations are examined next. Pulsars can emit regular pulses, matter sources, which are natural regions where molecules amplify microwave radiation, can produce narrow spectral lines. Stars with magnetic activity can create bursts. Interstellar gas clouds can emit at known frequencies. Some sources vary over time, some appear only under specific conditions. The candidate is compared with catalogues of pulsars, masers, variable stars, active galaxies, and known radio transients. The frequency does not match a simple known molecular line in the observed direction. The timing is not consistent with a standard pulsar. The bandwidth is narrower than most broad natural bursts. These facts do not prove artificial origin, but they leave fewer natural explanations. The signal structure becomes the center of attention. It repeats in blocks separated by pauses. Each block contains small changes in intensity, as though the energy is being shaped deliberately. The shaping is not understood as language, but it is measurable as order. A random process can produce patterns for a short time, yet repeated order across multiple observations is less easily dismissed. Scientists test the sequence against known forms of instrumental noise. They look for patterns caused by sampling rates, digital clocks, power systems, and software filters. If a signal repeats because of a machine on Earth, it may align with ordinary engineering cycles. This signal does not clearly align with such cycles. The detection teams treat the word artificial with care. In science, artificial means produced by technology or deliberate control, not simply unusual. A signal can be unexplained without being artificial. The distinction protects the analysis from reaching beyond the evidence. The working description remains a structured narrow-band radio signal from a fixed region of the sky. The phrase is plain, but it carries weight. It means the signal has survived several tests. It means it has direction, frequency structure, and repeatability. It also means that unknown natural causes remain possible. The region of the sky is examined with greater precision. Using the timing difference between observatories, researchers reduce the possible source area. The area contains many faint stars, some catalogued and some too dim for older surveys. Dust lies across part of the field, reducing visible light from more distant objects. Infrared surveys show cooler stars and possible background sources. No single object is immediately identified as the source. This absence does not weaken the radio detection by itself. Many radio sources are faint or distant in visible light. It does, however, slow interpretation because a source without a clear host cannot yet be placed in a physical setting. The signal is recorded again. This later detection is weaker, but the same internal timing appears. The frequency has shifted by a small amount. consistent with expected motion if the source is distant and if Earth's changing position is considered. The repeated blocks now allow more detailed study. Researchers search for a starting marker, an ending marker, and internal divisions. They find that the blocks begin with a simple pulse pattern repeated several times. After the opening pattern, the signal changes into a longer sequence of varied pulses. The opening portion appears more regular than the rest, as though it is intended to draw attention. This interpretation remains cautious, stated as a pattern rather than a purpose. Verification requires openness to error. Independent teams receive the data without the first team's full interpretation. They analyze the records separately and report similar findings about direction and structure. Their software is different. Their assumptions differ. The agreement strengthens the result. Disagreements remain in the details of frequency drift and source motion. Some models place the source at interstellar distance. Others cannot fully exclude a more complex source within the solar system, though known objects and spacecraft do not match. The scientific record therefore advances in measured language. At this stage, the signal becomes the first confirmed artificial pattern, only in the limited sense that its structure cannot be explained by known natural or human-made sources after repeated observation. The confirmation is not of beings, intentions, or a complete message. It is confirmation of a persistent pattern requiring a technological explanation or an unknown physical process with unusual order. The difference remains central. The arrival is not dramatic in the instruments. It is a line, a rhythm, a set of numbers stored in archives. Its importance grows because the ordinary explanations fall away one by one. Within the measured quiet of the inner network, the signal stands as organized energy from a direction beyond familiar activity, and science begins to treat it as contact with something not yet understood. Inside the signal itself, the first region of meaning is not language but structure. The recorded pattern is treated as a physical object made of time, frequency, strength, and repetition. Scientists begin with what can be measured directly. The signal rises above the background, holds a narrow frequency range, then changes in small controlled steps. Each step has a duration. Each pause has a duration. Each block returns with a similar beginning, before any attempt is made to assign meaning. The pattern is reduced to a sequence of measurable intervals. The simplest way to study the signal is to convert it into symbols based on presence and absence. A pulse becomes one value, a pause becomes another. This does not assume that the sender uses the same symbols. It only gives researchers a stable way to describe the pattern. When the pulses are arranged in order, they show repeated groupings. Some groups are short and simple, others are longer and irregular. The short groups appear at the beginning of each transmission block, and they remain more stable across observations than the longer portions. This makes them useful as markers. The opening marker contains repeated counts. A count is not a word. It is a pattern of separate pulses that can be compared across time. The counts do not follow ordinary human timing systems, and they are not tied to seconds in any necessary way. They become clear only after the signal is corrected for motion and stretched into its natural rhythm. Once this is done, the opening marker shows a sequence that can be divided cleanly into small prime numbers. A prime number is a whole number greater than one that can be divided evenly only by itself and one. Prime numbers are often considered useful in attempts at interstellar communication because they are not shaped by local culture. The presence of prime number groupings does not prove intention by itself. Nature can produce sequences that appear meaningful when examined too closely. Researchers therefore test many possible divisions of the signal. They ask whether the prime pattern remains under different methods of correction. They test whether the same grouping appears in separate detections. They compare it with random noise shaped by the same instruments. The result remains stable. The first portion of the signal repeatedly contains a pattern that is easier to describe through prime counts than through noise, known interference, or natural variation. After the opening marker, the signal becomes denser. Pulses vary in length and spacing. Some sections repeat exactly, others differ in a controlled way. Scientists examine whether the longer sequence can be arranged into a two-dimensional grid. This method has been considered in human-designed messages because a long stream of pulses can form an image or table when its length is factored into rows and columns. The signal length has several possible divisions, but only one arrangement produces broad areas of symmetry and repeated alignment. This does not create a clear picture, but it reveals ordered blocks, as if the sequence contains separate fields of information. Frequency also carries structure. The signal is not merely turned on and off. Its central frequency shifts in tiny steps during certain parts of the sequence. These shifts are small enough to remain within the same narrow band, yet consistent enough to act like an additional layer. The changes may represent values, corrections, or markers. They may also be a side effect of the source's motion or transmitting system. To separate these possibilities, researchers compare the frequency shifts with the timing shifts. Some changes match expected motion. Others remain after motion is removed. Those remaining changes become part of the signal's internal structure. The work continues through redundancy. Redundancy means the same information appears more than once, often in slightly different form. Redundancy is useful in communication because it protects meaning from damage. The signal shows repeated blocks that are not perfectly identical. Some parts appear unchanged, while others vary. This suggests that the stable parts may define a frame or key, while the changing parts may carry content. The interpretation remains limited. The pattern can be described, but its purpose is not yet known. Scientists also look for references to universal physical quantities. A message intended for an unknown receiver might use constants found everywhere in nature, such as the behavior of hydrogen, the speed of light, or ratios based on atomic transitions. The signal's frequency lies near a range that attracts attention because hydrogen, the most common element in the universe, emits a known radio line at a wavelength of about 21 centimeters. The candidate signal is not exactly this natural line, and it does not appear to be ordinary hydrogen emission. Still, its placement near a familiar astronomical reference may be significant, or it may be coincidence. The evidence is recorded without forcing a conclusion. Timing provides another possible layer. The pauses between blocks follow a pattern that seems too regular to be accidental, yet not tied to Earth-based units. When measured in relation to the signal's own smallest stable pulse, the pauses form ratios. A ratio is a comparison between quantities. These ratios repeat across separate observations. They may serve as punctuation, separating one block from another. They may also reflect limits in the transmitter, rotation of the source, or an orbit. Because physical systems can also create regular timing, researchers keep several explanations open. The longer sequence is examined for compression. Compression means reducing information by removing repeated parts or using short codes for common patterns. If the signal uses compression, it may be difficult to interpret without a key. The data shows repeated fragments, but not enough to prove compression. It also shows sections that resemble error correction, a method used to detect or repair mistakes in transmitted data. Error correction can be recognized when extra patterns appear at regular intervals and relate mathematically to nearby data. Some parts of the signal fit this idea, though not completely. The first meaningful breakthrough is modest. The opening marker is not translated into speech or warning. It is understood as a stable mathematical frame. It establishes that the sender, if there is a sender, can produce controlled radio energy and arrange it in repeated numerical form. It also gives scientists a basis for aligning different recordings. Once the marker is used as a reference, the longer sections can be stacked and compared. Damaged or weak portions become clearer when repeated transmissions are overlaid. The signal begins to resolve, not as a voice, but as an organized set of layers. The scientific community remains careful about naming. The pattern is described as possibly communicative because it contains features consistent with intentional signaling. It is not described as fully decoded. It is not described as a complete message from beings with known motives. The data supports order, repetition, mathematical framing, and internal variation. It does not yet support emotional meaning. The signal's first inner layer is therefore a grammar of measurement. Time becomes count, frequency becomes position, repetition becomes alignment. Within that alignment, uncertainty remains, but the shape of communication begins to appear in the quiet language of numbers. From the structure of the signal, attention moves inward toward its apparent stellar origin. This source is not found by imagination but by repeated measurement of direction, timing, and frequency drift. Each detection gives a line of sight across the sky. Each observatory adds a slightly different line. When these lines are combined, they narrow the possible region to a small field containing several faint stars and background sources. The field lies along a crowded part of the Milky Way, where dust and distance make identification difficult. The task becomes one of placing an organized radio pattern within a real astronomical neighborhood. The first step is astrometry, the measurement of positions and motions of objects in the sky. Star catalogues from space observatories provide exact locations for many stars, along with their apparent brightness, color, and movement over time. A star's proper motion is its slow change in position across the sky, caused by its movement through space relative to the Sun. Parallax is a small apparent shift caused by Earth's orbit around the Sun, and it allows distance to be measured for nearby stars. Together, these measurements turn points of light into physical objects with distance, motion, and sometimes size. Within the narrowed field, one star receives careful attention because its position best matches the corrected signal direction. It is dim in visible light, brighter in infrared wavelengths, and catalogued as an old, cool star. Cool in astronomy does not mean cold in an ordinary human sense. It means the star's surface temperature is lower than that of the Sun, giving it a redder color and weaker visible brightness. Such stars can live for many billions of years because they burn their fuel slowly. Their long lifetimes make them important in discussions of planetary stability, although their magnetic activity and radiation histories must also be considered. The star is not close to Earth. Its distance is measured in hundreds of light years, placing it far beyond the reach of any spacecraft now moving through the solar system. A signal from that distance carries information from the past. The radio waves now arriving left the source centuries ago. This delay is not a detail but a central physical fact. The star being observed in the present sky is also being seen as it was when its light began the journey. The signal belongs to that same earlier time. Any interpretation must remain tied to the age of the arriving radiation, rather than to assumptions about the source's current state. Spectroscopy provides more detail. Spectroscopy is the study of light separated into its colors or wavelengths, revealing the fingerprints of atoms and molecules. The star's spectrum shows hydrogen and helium, as expected, along with heavier elements in small amounts. Astronomers call elements heavier than helium metals, even when they are not metals in everyday language. The amount of these heavier elements matters because planets form from material left over around young stars. A star with enough heavier elements is more likely to have rocky planets, though it does not guarantee them. The star's age is estimated through several methods: its motion through the galaxy, its chemical composition, its rotation, and its level of magnetic activity all provide clues. Older stars often rotate more slowly and show different patterns of activity than younger stars. The measurements suggest a mature system, older than the Sun or at least not young. This does not mean the system is quiet. Cool stars can produce flares, which are sudden releases of magnetic energy. Flares can affect nearby planets by increasing radiation and stripping atmospheres over long periods. The observed star shows low activity during the measurement period, though past activity remains uncertain. The signal's frequency drift is compared with the motion of this star. If the source is near the star, the received frequency is affected by the star's movement relative to Earth. The measured drift does not match the star alone. It contains smaller variations that may be caused by a transmitter located on a rotating planet, an orbiting platform, or another moving body in the system. These possibilities remain physical models, not conclusions. The important point is that the signal's behavior is compatible with the source associated with the star, while most nearby catalogued alternatives fit less well. Astronomers examine whether the radio source could instead be a background object, such as a distant galaxy, quasar, or active galactic nucleus. A quasar is a very bright center of a distant galaxy, powered by material falling toward a supermassive black hole. Such objects can emit strong radio waves and vary over time. However, their signals usually show different spectral behavior and broader emissions. The candidate signal remains narrow and patterned. A background object is not impossible, but it becomes less likely as the repeated mathematical structure remains aligned with the star's position. The field also contains dust. Interstellar dust absorbs and scatters visible light, making some objects appear dimmer and redder. Infrared observations are useful because infrared light passes through dust more easily. These observations reveal no bright hidden stellar cluster at the exact source position. They show the cool star, a few faint companions at wider angular separation, and diffuse background emission. The absence of a dense cluster helps reduce confusion, although faint objects below detection limits may still exist. The possible source star is examined for companions. Many stars exist in binary or multiple systems, where two or more stars orbit a common center of mass. A nearby stellar companion can disturb planetary orbits or influence the environment through radiation and gravity. Current observations do not show a bright close companion, but small or dim companions cannot be completely excluded. The star's measured motion does not display a large wobble that would indicate a massive close companion. This supports the possibility of a relatively stable planetary system, though direct confirmation requires more data. The signal's apparent repetition period is compared with possible planetary or orbital periods. A planet rotating beneath a transmitter could cause the signal to appear and disappear as the transmitter turns into and out of view. An orbiting transmitter could create periodic changes as it moves around the star or a planet. A rotating beam could also explain intervals. The data is not yet sufficient to distinguish among these models. It only shows that the repetition is stable enough to be connected with motion in a gravitational system rather than random bursts. No visual beam, flare, or matching optical flash is detected from the star during the radio observations. This absence is expected for many radio sources. A transmitter designed for radio communication need not produce visible changes. Natural radio sources also may lack obvious optical counterparts. The lack of visible activity therefore neither confirms nor denies the association. It simply keeps the focus on the radio data and the measured properties of the star. The star's place in the galaxy is ordinary in the most important way. It is not in a dense young cluster, not near a known supernova remnant, and not close to the active centre of the Milky Way. It lies in a region where old stars move steadily through the galactic disk. This ordinary setting matters because it reduces some extreme explanations. The environment is not free from radiation or disturbance, but it is not among the most violent known regions. A stable star in a stable part of the galaxy can allow long planetary histories, though stability alone does not imply life or technology. As the source region becomes more defined, the signal gains a location without yet gaining a voice. The outer idea of a pattern becomes tied to a star with measurable light, motion, age, and chemistry. The star does not reveal intention, it reveals context. It shows that the signal, if truly associated with it, comes from a place governed by the same physics that shapes the sun and planets. Gravity organizes matter, radiation carries energy, dust dims light, motion shifts frequency. Across hundreds of light years, these rules allow a faint pattern to be traced back to a dim red star, old and steady in the measured sky, holding within its unresolved light the next layer of inquiry. Around the identified star, the planetary context becomes the next inward region of study. The star is too distant for its planets to appear as clear disks in ordinary images, so their presence must be inferred through indirect methods. Astronomers look for small changes in starlight, small motions of the star, and patterns in infrared emission. A planet can reveal itself by passing in front of its star and blocking a tiny fraction of light. This is called a transit. A planet can also reveal itself by pulling slightly on the star as both move around their shared centre of mass. This motion can shift the star's spectrum in a regular rhythm. Neither method is simple at such distance, but both provide ways to turn faint variations into a map of hidden bodies. The star's light shows evidence of more than one possible planet. The clearest signal belongs to a large outer planet, likely a gas-rich world with no solid surface like Earth's. Its orbit is wide and slow, and its gravity may influence smaller bodies in the system. A second, weaker pattern suggests a smaller planet closer to the star. This possible planet receives special attention because its orbit may place it within a temperate zone, where surface temperatures could allow liquid water under suitable atmospheric conditions. This region is often called the habitable zone, meaning a range of distances where liquid water could exist on a rocky surface. The term does not mean a planet is inhabited. It only describes one necessary environmental condition. The habitable zone around a cool red star lies closer to the star than Earth lies to the Sun. Because the star emits less energy, a planet must orbit nearer to receive comparable warmth. Close orbits can create tidal effects. Tidal forces arise when gravity pulls more strongly on one side of a body than the other. Over long times, these forces can slow a planet's rotation until the same side always faces the star. This state is called tidal locking. A tidally locked planet may have a permanent day side and a permanent night side, with climate shaped by atmospheric and oceanic circulation. Such a world is not automatically uninhabitable, but its conditions differ from Earth's. The possible inner planet's orbit appears stable within the limits of current data. Stability means that gravitational interactions do not quickly throw the planet into the star, into another planet, or out of the system. Long-term stability depends on the masses and spacing of planets, the presence of companions, and the history of the system. Computer models explore many possible arrangements, changing planetary masses and orbits within the uncertainties allowed by the observations. Many arrangements remain stable for long periods, some do not. The stable cases support the idea that a rocky planet could remain in place long enough for climate and geology to develop. The large outer planet may play several roles. In some systems, a giant planet can scatter comets inward or outward. It can shape belts of debris. It can also protect inner planets from some impacts while sending others toward them. Its effect depends on its orbit, mass, and relationship with smaller bodies. The observations suggest that the outer planet's path is not extremely elongated. A less elongated orbit is usually less disruptive. This does not prove a calm system, but it allows models in which the inner region remains orderly. A debris belt may also exist. Infrared measurements show a faint excess of warmth beyond what the star alone should produce. Such excess can come from dust grains warmed by starlight. Dust in a planetary system may be created by collisions among asteroids or comets. It may form a broad belt, similar in concept to the solar system's asteroid belt or Kuiper belt. The dust level appears moderate rather than extreme. A very dusty system could suggest heavy bombardment or recent collisions. A moderate belt suggests continuing small body activity without requiring a recent large disruption. The radiation environment is central to the planet's context. Cool red stars can be active, especially when young. Flares release ultraviolet radiation and charged particles that may erode atmospheres or alter surface chemistry. Over billions of years, a planet close to such a star may lose water if its atmosphere is not protected by gravity, magnetic fields, or replenishment from volcanic activity. The observed star appears quiet during current measurements, but the past remains uncertain. A planet's present habitability depends not only on today's radiation, but on the full history of stellar activity. The planet's possible mass and size remain uncertain. If the transit signal is real, the slight dimming of the star gives an estimate of the planet's radius. If the stellar wobble is measured, it gives a minimum mass. Combining radius and mass can suggest density, which helps distinguish rocky worlds from gas-rich mini-Neptunes. Current data permits a rocky interpretation but does not force it. A planet slightly larger than Earth may still be rocky, or it may hold a thick envelope of gas. The difference matters because a deep gas layer can prevent Earth-like surface conditions. The orbital period is measured in days rather than years because the planet lies close to its dim star. Written in physical terms, it circles its star many times during one Earth year. This closeness affects seasons, tides, and the amount of energy received. If the planet's orbit is nearly circular, its climate may receive steady input. If the orbit is more stretched, the planet may experience stronger changes in heating. Observations currently favor a near-circular orbit, though small deviations remain possible. No direct surface is visible. The planet is still a set of shadows, motions, and modelled possibilities. Yet the signal's frequency variations are compared with the planet's possible rotation and orbit. Some of the radio pattern fits more naturally if the source is associated with the inner planet rather than with the star itself. The fit is not absolute. A transmitter in orbit, a source on a moon, or an artificial platform elsewhere in the system could produce similar effects. The planetary model is treated as a working frame, not a final answer. In this inward layer, the unknown signal gains a possible world. The star becomes a system, and the system becomes a set of gravitational relationships. There is a dim primary star, a likely outer giant, possible dust, and a smaller world in a region where temperature may allow liquid water if the air and surface permit it. Nothing in this region confirms life, intelligence, or warning. It establishes only the physical stage on which such questions can be examined. The planet remains unresolved, but its orbit, light, and motion provide the next boundary of understanding. The message, still mathematical and distant, now seems tied to a place where rock, gravity, radiation, and time may have shaped a long planetary history. Within the possible planetary system, attention moves inward from orbits and masses to the air that may surround the smaller world. Atmosphere is the layer of gases held by a planet's gravity. It can shape temperature, protect a surface from radiation, move heat from one region to another, and carry chemical signs of geology or life. At the distance of the identified star, no telescope sees the atmosphere directly as a visible shell. Instead, scientists study changes in starlight when the planet may pass in front of the star, and they search for faint fingerprints of gases in the light that filters through or reflect from the planet. The main method is transmission spectroscopy. During a transit, a small part of the star's light passes through the edge of a planet's atmosphere before reaching Earth. Molecules in the air absorb specific wavelengths. When the light is separated into its spectrum, those missing parts can reveal which gases may be present. The signal is very small. It must be separated from the star's own changing surface, from instrument noise, and from the effects of dust between the stars. For a cool red star, this work is both useful and difficult. The planet blocks a larger fraction of the smaller star's light than Earth would block from the Sun, making atmospheric study easier in principle, but stellar activity can add confusing features. The first atmospheric evidence is cautious. Observations suggest absorption that may be consistent with water vapor, carbon dioxide, and possibly methane, but the measurements are not strong enough to declare a complete atmosphere. Water vapor can indicate evaporation from oceans, ice, or wet rocks, but it can also exist in many non-living environments. Carbon dioxide is common in planetary atmospheres and can come from volcanoes, chemical reactions, or earlier formation processes. Methane can be produced by biology on Earth, but it also forms through geological and chemical pathways. Each gas has meaning only within the whole pattern. A planet close to a cool star faces the question of atmospheric survival. High-energy radiation and charged particles can heat upper air and allow gases to escape into space. Smaller planets with weaker gravity are more vulnerable. A magnetic field may reduce some particle loss, but it does not provide complete protection. Volcanic outgassing can replace some gases over time if the planet remains geologically active. Impacts from comets and asteroids can also deliver or remove volatiles, which are substances that evaporate easily. Whether the planet keeps air depends on a balance among loss, supply, gravity, temperature, and stellar history. The detected pattern does not resemble a thick hydrogen atmosphere. Hydrogen is light and produces broad features when abundant. A planet with a deep hydrogen envelope would likely behave more like a small gas-rich world than a rocky planet with a surface atmosphere. The present data favours a heavier atmosphere if the signal is real. A heavier atmosphere may contain nitrogen, carbon dioxide, water vapour, oxygen-bearing compounds, or other gases. Nitrogen is difficult to detect directly from far away because it has weak spectral features. but it can still dominate an atmosphere, as it does on Earth. Clouds complicate the view. High clouds or haze can flatten spectral features, hiding the gases below. Haze can form when ultraviolet light changes methane and other molecules into complex particles. Around a cool red star, the color and energy of starlight differ from sunlight, and this can change atmospheric chemistry. A hazy atmosphere may show muted signals even if many gases are present. A clear atmosphere may reveal stronger features. The current observations allow both partial haze and partial clarity. The planet does not yet show the clean signature of a simple atmosphere. The possible presence of water vapor receives careful attention but not certainty. Liquid water on a surface can supply water vapor to air, yet water vapor can also come from steam atmospheres, icy surfaces, or high-altitude chemistry. If the planet is tidally locked, water may move through climate cycles very different from Earth's. On the day side, heat can drive evaporation. On the night side, cold can trap ice. Winds may carry vapor around the planet. Oceans, if present, could gather beneath clouds or along regions where day and night meet. These possibilities remain models, not observations. Carbon dioxide offers another clue because it helps control surface temperature through the greenhouse effect. The greenhouse effect occurs when certain gases absorb outgoing infrared radiation and keep a planet warmer than it would otherwise be. Too little carbon dioxide may allow freezing. Too much may trap excessive heat. Around a dim star, a planet may need some greenhouse warming to maintain liquid water, depending on its orbit and reflectivity. The suggested carbon dioxide feature is compatible with several climate states, from cool and stable to warm and dense. The data does not choose among them. Oxygen is treated with special caution. On Earth, abundant oxygen is strongly linked to photosynthesis, the process by which some organisms use light to build chemical energy and release oxygen. Yet oxygen can also build up without life under certain conditions, especially if water is broken apart by radiation and hydrogen escapes to space. Such false positives are important in astrobiology, the study of life in the universe. The current atmospheric evidence does not show strong oxygen. There are weak hints in some models, but they are not reliable enough to carry biological meaning. The absence of strong oxygen also does not rule out life, because life can exist without producing much oxygen. Methane, if present with carbon dioxide, would be chemically interesting. In an atmosphere exposed to starlight, methane tends to break down over time unless it is replenished. Replenishment could come from geology, such as reactions between water and certain rocks, or from biological activity, as on Earth. The observations suggest a possible methane feature, but the confidence is low. Researchers therefore describe it as a candidate gas, not a detection. Its importance lies in the need for future comparison with other gases. The atmosphere may also carry signs of change. Repeated observations taken during different transits show small differences in the strength of some features. These differences may result from instrument limits, star spots, clouds, or actual weather. Star spots are cooler regions on a star's surface caused by magnetic activity. When a planet crosses in front of them, the transit signal can be distorted. Because the star is cool and magnetically variable at low levels, star spots must be modelled carefully. Weather on the planet, if present, could also change cloud cover, but that explanation remains less certain than observational and stellar effects. The final message's source is not decoded through the atmosphere, but the atmosphere gives the planet a physical voice of its own. Light passing through gas carries a record of temperature, pressure, chemistry, and loss. The possible air around the planet appears neither clearly lifeless nor clearly living. It is a measured uncertainty. It may be thin or moderate. It may contain water vapor and carbon dioxide. It may hold haze. It may have changed across long spans under the influence of stellar radiation and geology. In this inward region, the world becomes less like a point in an orbit and more like an environment, still unresolved but increasingly real, with gases that may move, react, escape, and preserve traces of a history not yet understood. Beneath the possible atmosphere, the surface conditions of the planet become the next inward region of study. No telescope resolves mountains, seas, plains, or ice sheets directly. The world remains too far away, its light blended with the light of its star, its details hidden below the limits of current instruments. Yet surface conditions can still be approached through physics, the planet's size, mass, orbit, atmosphere, and received starlight place boundaries around what its surface may be like. Within those boundaries, scientists build careful models, always separating what observations indicate from what remains uncertain. A rocky surface is possible if the planet's density is high enough. Density is the amount of mass contained in a given volume. A dense planet is more likely to contain rock and metal. A lower density planet may contain more gas, ice, or a deep envelope of light elements. Current measurements allow a rocky world but do not fully exclude other forms. If the planet is rocky, gravity pulls material inward, forming a layered body with heavier metals likely concentrated toward the center and lighter, silicate rocks above. Such layering is common in planet formation, though each world develops according to its own history. The surface temperature depends on several linked factors. The star provides energy. The planet reflects some of that energy back into space. The rest is absorbed by the ground, ocean, ice, clouds, or atmosphere. Greenhouse gases then influence how much heat escapes. A planet near a cool red star may receive light that is redder than sunlight, with more energy in infrared wavelengths. Ice and clouds reflect this light differently than they reflect sunlight. These differences affect climate. A surface that appears bright under solar light may absorb more energy under redder light, changing the balance between freezing and warming. If the planet is tidally locked, one hemisphere may face the star most of the time while the other remains turned away. The day side would receive steady light. The night side would radiate heat into darkness. Without an atmosphere, the contrast between the two sides could be extreme. With a substantial atmosphere, winds could carry heat from the bright side to the dark side. With oceans, currents could also move heat, reducing extremes. Climate models show that tidally locked planets can hold stable conditions under some circumstances, especially if air and water circulate effectively. They can also freeze, overheat, or lose water under other circumstances. Liquid water remains a central surface question. It is important because all known life depends on it, and because it supports many chemical reactions. Liquid water requires pressure and temperature within certain ranges. A planet with too little air may allow water to boil away or freeze. A planet with too much heat may lose water to steam and then to space. A planet with enough pressure and moderate temperature may hold oceans, lakes, or wet ground. The atmospheric hints of water vapor do not prove liquid water. They only keep it within the range of possible surface conditions. The distribution of water would depend on rotation, topography, and climate. If the planet has continents and ocean basins, water may gather in low regions. If it is mostly ocean, it could form a water world with deep seas covering nearly all rock. If water is limited, It may exist as ice deposits, seasonal frost, underground reservoirs, or shallow basins near moderate zones. On a tidally locked world, ice may accumulate on the night side while liquid water persists where light and temperature are balanced. These patterns are possible outcomes, not confirmed features. Rock chemistry also matters. Silicate rocks can interact with carbon dioxide through weathering, a process in which minerals react with air and water. On Earth, weathering helps regulate climate over long times by removing carbon dioxide from the atmosphere and storing it in rocks. Volcanism can return carbon dioxide to the air. This cycle depends on liquid water, active geology, and surface exposure. If a similar process exists on the distant planet, it could stabilize climate over long periods. If it does not, the atmosphere may drift toward colder or hotter states. Volcanic activity is possible if the planet retains internal heat. Heat can come from leftover energy from formation, radioactive decay inside rocks, and tidal forces caused by gravity. A close orbit around a small star may produce tidal heating if the orbit is slightly stretched or if other planets disturb it. Moderate tidal heating can support geology. Too much can create intense volcanism and surface stress. Current orbital data do not show extreme tidal heating, but the uncertainties are large. A geologically active planet could refresh its atmosphere and create varied surface chemistry. The surface may also be shaped by impacts. Small bodies from a debris belt can strike planets over long times, delivering water and organic compounds or removing atmosphere through large collisions. Organic compounds are carbon-based molecules that can form through non-living chemistry and are not, by themselves, evidence of life. Impacts can sterilize local regions, melt crust, and create basins. They can also provide chemical ingredients and energy gradients. The amount of dust in the system suggests continuing small body activity, but not necessarily a destructive level of bombardment. Minerals on the surface would influence reflected light. Some minerals absorb strongly at certain wavelengths. Iron-rich rocks, clays, salts, and ices all leave different spectral signs. At present, these details are mostly below detection limits. Future instruments could search for broad patterns of reflectivity during different orbital phases, as the planet shows more of its day side or night side. Such phase curves may reveal clouds, oceans, continents, or ice indirectly. Current data are too limited for a surface map, but they allow scientists to define the questions. The possible radio source is examined in relation to the surface only through motion and timing. If the signal originates on the planet's surface, the planet's rotation would modulate its visibility. A fixed transmitter would face Earth only during part of each rotation, unless the beam is broad or relayed. If the planet is tidally locked, rotation and orbit are linked, changing the expected timing. The observed signal pattern can fit several geometries. A surface origin remains possible, but so does an orbital or off-world source. The evidence does not yet place the transmitter on land, ocean, ice, or structure. Surface conditions also define the limits of civilization in physical terms. Energy must be gathered, materials must be processed, waste heat must be released, and stability must be maintained against environmental change. A technological society on such a world would face the constraints of its star, its climate, and its geology. These constraints are not dramatic by themselves. They are the ordinary boundaries of planetary life. They determine where water can remain, where chemistry can proceed, where heat can be managed, and where long-term habitation might persist. In this inward region, the planet becomes a possible surface rather than only air in orbit. It may be rocky, It may hold water in one or more forms. It may have weathering, volcanism, ice, clouds, dust, and impact scars. It may be stable, stressed, dry, wet, frozen, or divided between extremes. Observations do not yet choose a single picture. They define a range in which natural processes operate. The signal remains above that range like a measured rhythm from an unresolved place. The surface below it, still unseen, becomes the ground on which chemistry, climate, and perhaps history may have unfolded. Within the possible surface environment, the next inward region is the question of a biosphere. A biosphere is the sum of living systems on a planet, including organisms, their environments, and the chemical exchanges between them. On Earth, life changes air, water, soil, and rock over long periods. It stores energy, releases gases, builds organic material, and alters the balance of elements. From far away, a biosphere cannot be seen as individual organisms. It can only be approached through patterns in chemistry, light, and change. The distant planet therefore offers no direct view of life. It offers only possible clues that must be held carefully. The first clue considered is atmospheric disequilibrium. Disequilibrium means that gases exist together in a state that should not last long, unless some process keeps renewing them. On Earth, oxygen and methane together are an example, because they react over time. Their continued presence requires replenishment. Biology provides much of that replenishment on Earth, but geology and sunlight can also create temporary or partial disequilibrium. For the distant planet, the suggested gases are not measured strongly enough to establish such a condition. Water vapor and carbon dioxide are plausible. Methane remains uncertain. Oxygen is not secure. The chemical case for life is therefore incomplete. The second clue is surface reflectance, the way a planet reflects starlight from its ground. Ocean, ice, clouds, and possible organisms. On Earth, vegetation reflects strongly in near-infrared light because of the structure of leaves and the chemistry of photosynthesis. This pattern is sometimes called a vegetation edge. It is not a universal sign of life. Alien organisms, if they exist, may use different pigments, different light, or no photosynthesis at all. Around a cool red star, available light differs from sunlight, so any photosynthetic surface might reflect in a different way. Current observations of the distant planet are too weak to detect such a pattern reliably. The third clue is seasonal change. A living planet may show repeating variations in gases or surface color as organisms grow, decay, or respond to climate. Earth's carbon dioxide, oxygen, and methane cycles carry biological influence. Though they are mixed with ocean and geological processes, on the distant planet, the observing period is too short and the signal too faint to establish seasons. If the planet is tidally locked, seasonal patterns may be limited or shaped mainly by orbital changes and atmospheric circulation. If its axis is tilted or its orbit is slightly elongated, climate cycles may occur. The evidence does not yet reveal them. Astrobiology begins from known life but does not assume that all life must look like Earth life. The safest foundation is chemistry. Life as known requires a liquid medium, a source of energy, and elements able to form complex molecules. Carbon is especially useful because it forms many stable bonds. Water is especially useful because it dissolves many substances and remains liquid over a wide temperature range under planetary conditions. Energy can come from starlight, chemical reactions, heat from the interior, or gradients between different environments. The distant planet may provide some of these conditions, But the presence of conditions is not the same as the presence of life. If the planet has oceans, possible habitats may exist at the surface where light enters water, or at the seafloor where rock and water exchange chemicals. On Earth, hydrothermal vents release heated, mineral-rich water and support ecosystems that do not depend directly on sunlight. Such systems show that life can be connected to geology as well as to light. A distant observer would struggle to detect such life unless it changed the atmosphere or surface on a large scale. Therefore, a planet could be inhabited and still appear ambiguous from far away. If the planet is dry or partly frozen, life would face different limits. It might survive in underground water, beneath ice, in salty films, or within rocks, if the chemistry and energy sources allow it. These forms would leave even weaker remote signs. A sparse biosphere may not produce enough gas to be detected across hundreds of light years. The absence of strong biosignatures therefore cannot be treated as absence of life. It only means that no global biological signal has been confirmed. The possible methane feature remains a focus because methane can be interesting in a carbon dioxide atmosphere. Without replenishment, starlight breaks methane apart. If methane is truly present, some process must supply it. Geological reactions can create methane when water interacts with iron-rich rocks under certain conditions. Impacts can add methane or related compounds. Volcanic systems can release reduced gases. Microbial life on Earth also produces methane in oxygen-poor environments. The distant data cannot distinguish among these sources. It only suggests that, if methane is real, the planet may be chemically active. Oxygen receives even greater caution. A strong oxygen signal with reducing gases could point toward biology, but oxygen alone can mislead. A planet that loses water may leave oxygen behind after hydrogen escapes to space. A dry world with little volcanic gas may allow oxygen to accumulate without life. Certain stellar radiation environments can increase this risk. Since the distant planet orbits a cool star with an uncertain early history, false oxygen scenarios must be considered. The weak oxygen hints in the data are not treated as biological evidence. The radio signal influences the biosphere question indirectly. A technological transmission would imply intelligence somewhere in the system, and intelligence as known arises from biology. Yet the signal itself cannot confirm a planetary biosphere. It may come from an old automated system, an orbital platform, a probe, or a source no longer connected to living organisms. It may also come from technology built by life that changed or disappeared before the signal reached Earth. Because of the time delay, present biology and the received transmission need not match. The evidence for life must therefore remain separate from the evidence for technology. Researchers search the decoded structure for possible biological references, but at this stage the signal still yields only mathematical framing and repeated data blocks. Some blocks may represent physical quantities, others may represent maps, chemistry, or timing. No biological term can be assigned. There is no secure image of an organism, no confirmed description of DNA, no clear statement of life. The restraint matters because human pattern recognition can turn ambiguous data into familiar shapes. Scientific interpretation requires that a biosphere be inferred from measurable environmental effects, not from desire or fear. On Earth, the history of life shows that a biosphere can transform a planet slowly. Early microbial life altered chemistry long before complex organisms appeared. Photosynthesis changed the atmosphere over immense spans of time. Geological cycles and biological cycles became connected. If a similar process occurred on the distant world, its traces may be distributed across air, rock, ocean, and climate. yet such traces may be subtle, damaged, or masked by non-living processes. The planet may have life, may once have had life, or may only imitate life through chemistry. In this inward region, the possible biosphere remains a threshold rather than a discovery. The world has conditions that may allow life under some models. Its air may contain gases of interest, its surface may support water under some climates, its star provides energy, and its rocks may provide chemistry. None of these points alone establishes living systems. Together they form a cautious field of possibility. The signal continues to suggest technology somewhere near the star. But the living foundation behind that technology remains unconfirmed. The planet's possible life is therefore described in quiet terms not absent, not proven, and not yet separable from the deep chemistry of a changing world. Within the uncertain boundary of a possible biosphere, the next inward region is the technological layer. Technology cannot be assumed from biology, and biology cannot be assumed from technology. Yet the signal itself requires attention to the ways a civilization may alter its surroundings. A technological layer is not a separate shell like an atmosphere. It is the set of measurable effects produced when intelligence uses energy, builds systems, processes materials, and sends information. From hundreds of light years away, these effects are difficult to see. They must be searched for in heat, light, chemistry, radio emission, and changes that do not fit ordinary planetary behavior. The radio signal remains the strongest evidence for such a layer. It is narrow, repeated, structured, and stable across observations. These features are consistent with a controlled transmitter. The energy required depends on how focused the beam is. A beam aimed narrowly toward the solar system could use far less power than a broadcast sent equally in all directions. A broad broadcast would require much greater energy to remain detectable across interstellar distance. Because the signal is not continuously strong, and because it appears in repeated blocks, researchers consider the possibility of a directed transmission, a rotating beam, or an intermittent system that sends only during certain windows. A directed beam implies knowledge of the target direction, or a survey pattern that sweeps across many stars. It does not necessarily imply that Earth was singled out. A transmitter could send the same message toward many possible receivers over long periods. A rotating beacon could cross Earth's line of sight at intervals, much as a lighthouse beam crosses a distant observer. An automated station could repeat a stored message without any living operator. These possibilities are treated as engineering models. They explain the timing and strength without requiring conclusions about intention. Technological activity also produces waste heat. All energy use eventually becomes heat, and this heat must be released into the environment or into space. A civilization using large amounts of energy may create an infrared excess, meaning more infrared radiation than expected from natural sources alone. Infrared surveys of the star system show a faint excess that can be explained by dust. The amount is not large enough to indicate a system-wide structure collecting most of the star's energy. It does not rule out smaller-scale technology. It only shows that no enormous heat signature is detected with current instruments. Artificial light is another possible sign. On Earth, city lights create a night-side glow. But detecting such light across interstellar distance is extremely difficult. A planet close to a dim red star may offer better contrast in some cases, yet the distant planet remains unresolved. The expected artificial light from ordinary cities would be far below present detection limits. Only unusually intense illumination or large reflective structures might be seen. Current observations do not show a confirmed artificial light pattern. The absence is expected and does not strongly affect the radio interpretation. Industrial chemistry may alter an atmosphere. Certain gases, if found in significant amounts, could suggest technological activity because they are not easily produced in large quantities by natural processes. On Earth, some industrial compounds are artificial and persist in air for long periods. Detecting such compounds around an exoplanet would be difficult, requiring high sensitivity and careful exclusion of unknown chemistry. The distant planet's atmospheric data are not detailed enough to identify industrial gases. The possible features remain water vapor, carbon dioxide, and uncertain methane, with no secure evidence of manufactured compounds. The technological layer may also involve satellites, orbital habitats, or power collectors. Such objects are too small to image directly at this distance, unless they are enormous or arranged in vast numbers. They might affect starlight during transits if they pass in front of the star, producing unusual dimming patterns. The observed transit data show no clear irregular shapes beyond the possible planet itself and ordinary noise. This does not exclude smaller structures. It only means that no large opaque structure has been detected. Radio leakage from ordinary communications is unlikely to be detected across hundreds of light years unless the source is powerful or focused. Human radio leakage fades quickly with distance and becomes hard to distinguish from noise. The detected signal is therefore unlikely to resemble casual background communication. It is more consistent with a deliberate beacon, radar-like system, or high-power transmission. This conclusion concerns engineering, not motive. A signal can be deliberate without being personal. It can be a warning, a record, a navigation marker, a scientific transmission, or an automated archive. The internal structure of the signal begins to reveal a technical frame. The repeated opening markers help align the data. After alignment, several blocks appear to represent physical constants and scaled quantities. The values are not written in human units. They are expressed as ratios related to the signal's pulse timing and frequency. Some ratios correspond closely to basic astronomical quantities that could describe the source system, including the star's rotation, the inner planet's orbital period, and a reference linked to hydrogen radiation. These correspondences are not perfect, but they are strong enough to guide interpretation. A later block appears to encode a map. It does not show pictures of landscapes or beings. It shows repeated coordinate-like groupings that match the relative positions of the star, the large outer planet, and the smaller inner planet under one model. The match improves when the time delay of the signal is included. This suggests that the transmission may contain information about its own origin. Scientists remain cautious because map-like interpretations can be shaped by expectation. Still, the structure has enough internal consistency to become a working hypothesis. The signal also contains a block that appears to describe energy flow. It uses repeating ratios that may correspond to stellar input, planetary heat balance, and emitted infrared radiation. If this interpretation is correct, the transmitter is not simply announcing presence. It is describing a planetary state. The values suggest a planet with increasing retained heat over a long interval, but the uncertainty remains large because the units and scaling are still being tested. Researchers do not yet call it a warning. They call it a physical sequence related to energy. Technology leaves signs not only through power, but through timing. Natural systems can be regular, but technological systems can maintain patterns across many cycles with controlled correction. The signal's repeated blocks show evidence of drift compensation. Over long transmission intervals, the source seems to adjust its frequency or timing to remain coherent. This could be done by an active transmitter, an automated clock, or a system designed with stable reference standards. Such coherence strengthens the case for technology. It also suggests that the transmitter is built to survive noise, motion, and distance. No conclusion is made about the makers. The data does not reveal bodies, social forms, intentions, or emotions. It does not show cities, machines, or faces. It shows controlled energy arranged in an ordered pattern. From a scientific point of view, that is enough to define a technological layer but not enough to describe a civilization. The layer may be active, decaying, automated, or historical. Because the signal is centuries old, its present condition is unknown. The received transmission is a fossil of activity, carried by light-speed delay into Earth's instruments. In this inward region, technology becomes measurable but still impersonal. It appears as narrow radio power, structured timing, possible system coordinates, and possible energy ratios. Other technosignatures remain absent or below detection limits. There is no visible megastructure, no confirmed artificial light, and no identified industrial gas. The signal alone carries the weight. It is a precise thread crossing interstellar space, not loud in energy but strong in order. Around the distant world, the technological layer is therefore defined by what can be measured a repeating transmission that seems to know physics, location, and perhaps the changing condition of its own planet. Within the technological layer, the next inward region is the evidence for decline. Decline is not treated as a story of sudden ruin or imagined catastrophe. It is approached as a set of possible changes in energy balance, atmospheric chemistry, surface stability, and signal behavior. A civilization, if it exists or once exists near the source star, must operate within a planetary environment. It gathers energy, uses materials, releases heat, and depends on systems that remain stable enough to support long-term activity. When these systems change beyond manageable limits, the traces may appear first as physical imbalance, rather than as any direct statement of loss. The signal's later blocks provide the first measured basis for this interpretation. After the mathematical markers, the coordinate-like structure, and the possible energy sequence, several sections repeat values that change in a steady direction. They appear to describe a system moving away from equilibrium. Equilibrium means a balanced state in which incoming and outgoing energy, or production and loss, remain roughly stable over time. A planet does not need perfect balance at every moment, but over long periods its climate depends on the relationship between absorbed starlight and heat released to space. If retained heat increases, surface and atmospheric conditions can shift. The decoded values are still uncertain because the message does not use human units. Researchers compare the ratios with several physical models. One model links them to atmospheric warming, another links them to increasing infrared opacity, which means the atmosphere becomes less able to let heat escape. A third connects them with changes in surface reflectivity, possibly from ice loss, cloud change, dust, or land alteration. None of these models is proven, yet each points toward a planet whose energy balance is changing. The repeated direction of the values matters more than any single number. They describe a trend, not an isolated event. Atmospheric evidence from telescopes gives a weak but independent context. The possible carbon dioxide feature may indicate a substantial greenhouse gas. The possible methane feature, if real, may indicate active replenishment. Neither observation confirms planetary stress. However, when compared with the signal's apparent energy sequence, they become part of a broader physical picture. The planet may have an atmosphere capable of trapping heat. It may have chemistry that changes over time. It may have clouds or haze that alter the way light is absorbed and reflected. These factors can push climate toward new states if feedbacks become strong. A feedback is a process in which a change reinforces or weakens itself. Ice provides a simple example. Bright ice reflects starlight. If ice melts, darker ground or water may absorb more energy, causing more warming. Clouds can either cool or warm depending on their height, thickness, and composition. Water vapor is also a greenhouse gas, so warming can place more vapor in the air, which can produce further warming under some conditions. Around a cool red star, these feedbacks may differ from those on Earth because the color of starlight changes how surfaces and clouds absorb energy. The signal does not show cities failing or populations moving. It shows physical sequences that may describe limits being crossed. One block appears to encode atmospheric loss or atmospheric transformation. The ratios resemble a comparison between lighter gases escaping and heavier gases accumulating, though this reading remains tentative. If a planet warms strongly, water vapor can rise higher in the atmosphere, where radiation may break water molecules apart. Hydrogen can escape into space more easily than heavier atoms. Over long periods, this can dry a planet. Such processes are known in planetary science and are discussed for worlds such as Venus and some close-orbiting exoplanets. Whether this exact process applies to the distant planet remains uncertain. Another block may describe biological reduction. The interpretation is weaker because biosignatures were never confirmed. The sequence includes changes that could correspond to decreasing chemical renewal, reduced surface productivity, or shrinking habitable zones. These terms are model-dependent and cannot be assigned with confidence. A non-living planet could produce similar chemical shifts through geology or photochemistry. For this reason, researchers do not claim the message proves dying life. They state only that one part of the transmission may describe a declining capacity for surface systems to maintain previous conditions. The technological interpretation becomes more grounded in the signal's own behavior. Across repeated observations, the opening marker remains steady, but the later data blocks show signs of archival repetition rather than active revision. The same sequence returns again and again without clear update. This may mean the transmitter is a beacon repeating a final stored message. It may also mean the message is intentionally fixed, designed for long-term recognition. The distinction cannot be resolved from the current data. A stored message does not prove that its makers are gone. It only shows that the transmission does not yet respond to reception from Earth, which would be impossible in any immediate sense because of the light speed delay. The phrase final message begins as a human label for the last major portion of the decoded sequence, not as a confirmed emotional statement. The final portion is set apart by a change in structure. The earlier blocks establish counting, origin, and physical context. The later blocks become repetitive and compressed, as if emphasizing a smaller set of relationships. These relationships seem to connect energy use, planetary heating, atmospheric change, and the narrowing of stable surface conditions. The order is plain and physical. It does not rely on images of disaster. It describes a system that cannot continue unchanged. Energy use may be central. Any technological society increases its influence on a planet by converting stored or incoming energy into work and heat. If energy use grows beyond the environment's ability to absorb changes, it can alter climate, chemistry, and ecosystems. This principle does not depend on the details of alien biology. It follows thermodynamics, the study of heat, energy, and work. Waste heat is unavoidable. Chemical byproducts may be avoidable or manageable, but only if systems are designed to remain within planetary limits. The signal's apparent energy block may be a record of a society recognizing that its own power systems have become part of its planet's climate. The decline may also involve external limits, a cool star's past activity, orbital tides, volcanic changes, impacts, or atmospheric escape may have stressed the planet before technology became important. The signal does not allow a simple blame. It may describe a world where natural vulnerability and technological pressure combine. This interpretation is scientifically cautious because planetary histories are rarely controlled by one factor: climate, geology, life. And technology can interact in ways that produce slow instability rather than sudden collapse. The surface models add another boundary. A tidally influenced planet may have habitable regions concentrated in certain zones. If warming, drying, or atmospheric loss shifts those zones, the area suitable for complex life or settlement may shrink. On such a world, habitability may not disappear everywhere at once. It may retreat into smaller regions, underground water, polar ice, night-side reserves, or engineered habitats. The signal does not state where inhabitants go. It only seems to describe environmental narrowing. The silence around social detail keeps the analysis centered on measurable conditions. In this inward region, decline is therefore not terror in the dramatic sense. It is the quiet recognition of limits written into physics. The possible civilization leaves a transmission that links its world to energy, air, heat, and time. The planet appears as a system under strain, though the exact cause and outcome remain uncertain. Observations indicate structured data consistent with planetary change. It remains uncertain whether that change is natural, technological, biological, or a combination of all three. The message continues inward, not toward spectacle, but toward a final core of relationships that describe what happens when a world's sustaining balances fail faster than they can be restored. At the core of the decoded transmission, the final message becomes smaller in form and heavier in meaning. It is not a speech, not a plea, and not a set of images arranged for human feeling. It is a compact structure of repeated physical relationships. Earlier portions of the signal establish counting, origin, planetary context, and signs of imbalance. The inner portion returns to those same ideas with less variation, as though the message has reduced itself to what can survive distance, noise, and time. The result is not dramatic in language. It is austere, mathematical, and calm. The first part of this core repeats the reference frame. The signal returns to prime number groupings, then to ratios linked with hydrogen radiation, the star's properties, and the planet's orbit. This repetition appears to serve as a key. It tells the receiver how to align the later values. Without it, the final blocks would be only changing pulses. With it, they become a set of comparisons. The form suggests that the sender expects no shared language, no shared culture, and no shared symbols beyond physics. The message relies on what light, atoms, gravity, and heat have in common everywhere. A central relationship appears again and again. Energy enters a planet from its star. Some is reflected, some is absorbed. Heat leaves the planet as infrared radiation. A long-term stable climate depends on the balance between these flows. The signal's values describe the absorbed part increasing relative to the escaping part, or the escaping part becoming less effective as the atmosphere changes. Researchers test both readings. The difference matters for details. But both point toward the same broad condition. The planet is retaining too much energy for its previous state to continue. The next relationship connects atmosphere and surface. The decoded blocks suggest a rise in gases that trap heat and a decline in surface reflectivity. This could mean darkening ground, loss of bright ice, changing clouds, expanding dust, altered oceans, or artificial surface change. It could also describe a model rather than a direct measurement, because the sender may be explaining what is happening rather than listing observations. The structure does not allow certainty. It allows a careful statement that the final message is consistent with planetary warming and reduced ability to release heat. The following block appears to describe water. The values are arranged in a way that resembles phase boundaries, the conditions under which water remains solid, liquid, or gas. Phase means the physical form of a substance. On a planet, water can freeze as ice, flow as liquid, or enter the air as vapor, depending on temperature and pressure. The sequence seems to show liquid water becoming less stable across parts of the surface. It does not state that all water is gone. It suggests that the range of stable liquid water has narrowed. In planetary science, that narrowing is a severe environmental change, especially for any biosphere that depends on open water. A deeper layer connects water to atmospheric escape. The signal includes ratios that may correspond to lighter atoms leaving the planet more easily than heavier ones. Hydrogen, being light, can escape from the upper atmosphere if water molecules are broken apart by radiation. Over long times, this can reduce a planet's water supply. The reading remains uncertain, but it is physically plausible. If correct, the message describes not only heat but loss. As a world gradually loses part of the material needed for surface stability, the final message does not name a cause in a simple way. It does not isolate technology, star, volcanoes, orbit, or life as the only driver. Instead, it links growth in energy use with changes in atmosphere and surface balance. The pattern suggests that technological activity has become large enough to affect the planetary system, while natural conditions may have made the system vulnerable. This is a more careful and more difficult conclusion than a single cause. It describes a civilization embedded in its planet rather than standing apart from it. Thermodynamics forms the quiet center of the warning. Energy cannot be used without consequence. Every machine, habitat, transmitter, factory, and computing system turns ordered energy into heat. Chemical changes may be controlled or reduced, but waste heat remains. A planet can release heat into space only according to its temperature, atmosphere, clouds, and surface. If energy use and atmospheric change push beyond what the system can release, the environment shifts. This principle is not a moral statement. It is a physical limit. The message then appears to compare timescales. One sequence may represent the time needed for atmosphere, ocean, and rock to restore balance. Another may represent the faster time over which technological energy use grows. When the second becomes much shorter than the first, adjustment fails. Geological systems often work slowly. Weathering, carbon storage, ocean mixing, and ice recovery can take long spans. Technology can change energy flows and chemistry much faster. The final message may therefore describe a mismatch between the speed of disturbance and the speed of repair. A separate block appears to contain a threshold. In science, a threshold is a boundary where a system changes behavior after a certain point. Below it, feedbacks may remain manageable. Above it, they may reinforce change. The decoded value suggests that the planet has crossed, or is approaching, such a boundary. The exact nature of the threshold is uncertain. It may involve water vapor, cloud change, ice loss, biosphere decline, or atmospheric escape. The message does not supply enough detail to choose one, It only indicates that the earlier stable state cannot be recovered by the same processes that once maintained it. The core becomes most direct in its final repetitions. The same relationships appear in shortened form, energy imbalance, atmosphere change, water narrowing, recovery time longer than damage time. The order repeats with minor variations, as though designed to survive partial loss. If one part is damaged, another carries the same meaning. This redundancy is not emotional, it is practical. It helps the message remain readable after centuries in space and after distortion by noise, motion. An incomplete reception. The word terrifying belongs to human interpretation, not to the signal itself. The message does not shout, it does not threaten, it does not describe monsters, invasion, or punishment. It presents a planet losing stability through processes that can be stated calmly. Its force comes from recognition. The same physics governs all worlds. Any civilization that uses energy at planetary scale must understand atmosphere, heat, water, and repair. The final message becomes frightening only because it is ordinary enough to be possible. It is not outside nature. It is nature followed to its limits. The last decoded block is the most compressed. It seems to state that knowledge arrived too late to restore the old balance. This reading is cautious, because the block is partly damaged and depends on the alignment established earlier. Yet many teams reach a similar interpretation. The message may be saying that measurement, understanding, and warning came after the planet had already entered a new state. It may also be saying that transmission itself is the remaining act, a record sent outward because local recovery is no longer assured. The distinction remains unresolved. There is no confirmed signature of extinction. There is no proof that the makers are gone. The message left centuries ago, and the present condition of the source system is unknown. The final portion can only be understood as a record from the time of transmission. It may come from a living civilization warning others. It may come from an automated archive after collapse. It may come from a scientific station recording planetary failure. The data does not decide among these possibilities. At the inner core, the final message is therefore not a sentence but a structure. It says, through physics, that a world can pass beyond the conditions that sustained it. It says that energy, air, water, and time are linked. It says that intelligence does not remove a civilization from planetary limits. It only gives that civilization the ability to measure those limits, cross them, or respond before they close. The transmission ends its core not with mystery but with balance lost. Written in ratios and repeated until the meaning survives the dark. Inside the human response, the signal becomes less a distant object and more a mirror held against Earth's own systems. The first reaction remains scientific. Data is checked again, not because the discovery is dismissed, but because the weight of interpretation demands restraint. Observatories repeat their measurements, archives are reviewed, independent teams reprocess the raw records. The decoded structure is tested against alternative explanations, including unknown natural sources, hidden interference and accidental mathematical patterns. The result does not become simpler, it becomes more carefully bounded. A structured transmission appears to come from a distant star system, and its inner content appears to describe planetary imbalance. Everything beyond that remains measured with caution. The response is shaped by the delay of light. The signal has travelled for centuries before reaching Earth. Any reply would require the same long crossing. A message sent now would arrive in a future that cannot be known by the senders on Earth. The source system may have changed greatly since the transmission began. The civilization that made the signal may still exist, may have transformed, or may no longer remain. This delay prevents the event from becoming an ordinary conversation. It is contact in the sense of reception, not exchange. It is a record from another place and another time. Scientific institutions begin by preserving the data in open and redundant forms. Multiple archives store the raw recordings, calibration files, telescope logs, atmospheric records, and processing methods. This is necessary because interpretation may change as instruments improve. A later generation may detect details that current methods miss. The signal is therefore treated not only as an event, but as a long-term scientific object. Like ancient light from distant galaxies or samples from the moon, it becomes material for repeated study. The ethical response develops more slowly. A transmission that appears to describe planetary failure does not give direct instructions, yet it changes the scale of responsibility. It shows that intelligence, if the interpretation is correct, can reach high technical ability and still remain vulnerable to the physical limits of its world. The message is not used as proof of a single human policy. It cannot decide economics, governance, technology, or culture. It can only widen the frame. It places human activity within the same laws of energy, atmosphere, water, and time that govern every planet. Public understanding requires careful language. The signal is not presented as invasion, prophecy, or certain extinction. It is described as a structured interstellar transmission with content consistent with environmental warning. Scientists explain what is known and what remains uncertain. They explain that the source is far away, the message is old, and the makers are unknown. They explain that the warning is physical, not supernatural. This careful communication matters because fear can distort evidence as easily as hope. The calm statement of limits becomes more useful than dramatic certainty. Earth's own observing systems turn inward as well as outward. Climate satellites, ocean monitors, atmospheric stations, ice measurements, and biodiversity surveys already track changes across the planet. After the signal, these systems gain a new symbolic weight, though their scientific purpose remains the same. They measure the balance of energy entering and leaving Earth. They measure greenhouse gases, clouds, forests, oceans, ice sheets, and land use. They do not need the alien signal to be valid. Their evidence stands on its own. The distant message only reminds humanity that measurement must lead to understanding before change becomes harder to reverse. The comparison between Earth and the distant planet is handled with discipline. Earth orbits a different star, has a different atmosphere, a different history, a large moon, active plate tectonics, oceans, and a biosphere known in detail. The distant world remains uncertain in nearly every specific feature. Direct equivalence would be scientifically weak, yet the general principles are shared. Energy balance matters, atmospheric composition matters, water stability matters, feedbacks matter, recovery times matter. A civilization cannot ignore these principles simply because its planet differs from another. A response from humanity is debated, but the debate remains constrained by physics. Any reply would be symbolic across centuries. It could acknowledge receipt, share mathematical understanding, describe Earth's location, or send scientific data. It could remain silent while observation continues. There is no immediate rescue, no direct warning returned in time, and no practical exchange of assistance. The value of a reply would lie in continuity, not solution. It would say that the signal was received by another technological world capable of recognizing the pattern. The strongest response, however, is not outward. It is inward toward Earth's own future. The final message's core relationships are compared with known planetary science. They become a teaching structure. Energy use must be understood within climate limits. Atmosphere cannot be treated as empty space. Water stability is fragile under enough pressure. Repair processes may be slower than damage. These lessons are already present in human science, but the signal arranges them in a stark and distant form. It removes the assumption that technological intelligence automatically guarantees long survival. The human mind often seeks intention in a message. It looks for fear, regret, command, or accusation. The decoded signal does not provide those things. It gives relationships. This absence becomes part of its meaning. The sender, whether living or automated, chooses the language of physics because it has the best chance of crossing distance. It does not ask to be mourned. It doesn't ask to be obeyed. It leaves a record of limits. Humanity receives that record and must decide how to carry knowledge without turning it into myth. At the deepest point of the response, Earth is seen as a layered system rather than a stage for isolated human action. There is space around it, a magnetosphere shaped by the sun, an atmosphere moving heat and water, oceans storing energy, rocks exchanging gases, ice reflecting light, and life-changing chemistry. Human technology is now part of that system. It is not outside nature. It draws power, moves materials, changes land, releases gases, and produces heat. This recognition does not diminish intelligence. It places intelligence where it belongs, inside the planet that supports it. The signal from the distant star continues to arrive in repeated windows. Each reception confirms some parts and leaves others unresolved. The message does not become comforting, but it becomes clearer in its restraint. It shows that knowledge can cross darkness even when certainty cannot. It shows that a final act of measurement may outlast the world that made it. It shows that contact with another intelligence may not begin with greeting, but with evidence of consequence. In this final section, the path has moved inward from galaxy to star, from star to planet, from planet to atmosphere, from atmosphere to surface, from surface to life, from life to technology, and from technology to responsibility. The first contact does not end with an answer about who they are. It settles instead into the question of what any technological species becomes when it understands the limits of its home. On Earth, the message remains in archives, in models, in public memory, and in the quiet work of instruments measuring the planet each day. The final message from far away becomes a human responsibility, not because it commands action, but because it describes a law that no world can escape. The signal remains in the records, steady and distant, while Earth turns beneath its own sky. The galaxy continues around it, filled with stars that move slowly through dust and darkness. The message from the old red star does not change the laws of nature. It only reveals them through another world's history, carried across space as ordered radio light. Human instruments keep listening. Antennas gather faint waves. Telescopes measure dim stars. Satellites watch clouds, oceans, ice, forests, and heat. Each measurement is small, but together they describe the planet that holds all human life. The distant message rests beside these measurements, not above them. It becomes another reminder that air, water, rock, energy, and living systems are joined. No face appears from the signal. No voice crosses the distance. The first contact is a pattern, a warning shaped by physics, and a record of a world that may have learned too late. Its meaning remains calm and severe. A planet can carry life for a long time. A civilization can learn to measure its home. Knowledge can arrive before change closes the path, or after. Earth remains bright in the dark, wrapped in air, warmed by the sun, and balanced by processes that work slowly. The message settles into that balance like a quiet mark in memory. It asks for no fear, only attention. It leaves no command, only relation, energy, atmosphere, water, and time remain together. The listening continues, and the night grows still around it.